single-mode fibers. Single-mode fibers provide higher bandwidth than multi-mode fibers. The wavelengths supported by these have lower attenuation than the wavelengths supported by multi-mode fibers, making single-mode fibers ideal for long-distance and high-bandwidth applications like telecom, data centers, and cable television. Single-mode fibers have cores that are approximately 9 microns in diameter. These fibers support high-bandwidth laser-based systems designed for long-distance applications like telecommunications. Fiber performance can be critically impacted by chromatic dispersion, which could be a bandwidth and distance limiting factor. In general terms, chromatic dispersion is caused by wavelength speed variations, as longer wavelengths travel faster than shorter ones. Chromatic dispersion is affected by multiple factors including material dispersion, waveguide dispersion, and transmitter emission spectrum. Material dispersion is caused by the differences in wavelength speeds as these travel through the fibers. The longer the wavelength, the faster it will be, as well as tolerant to attenuation, therefore increasing distance reach. Waveguide dispersion occurs due to small amounts of light traveling through the cladding of the fiber at slightly different speeds than in the core, causing signal deterioration over time or distance. Most fiber optic transmitters produce signals with multiple wavelengths referred to as spectral output. Some transmitters are engineered to have restricted outputs to reduce chromatic dispersion. The less precise the transmitter or the broader its spectral output, the lower the signal quality, impacting its bandwidth and distance reach. In long-distance links, transmitters use lasers with very narrow outputs to limit issues with dispersion and ensure signal quality. Polarization mode dispersion, or PMD, refers to optical signal degradation due to components of the light traveling at different speeds, and it's caused mainly by imperfections in the geometry of the fibers. Though it might be easy to imagine light signals traveling in straight lines, in reality, light travels in patterns that resemble waves stretching and contracting in sharp angles or polarized states as they travel. A perfectly rounded core might avoid PMD issues. However, imperfections in the geometry of the core, as well as movement from wind in aerial installations, or vibrations like those produced by passing trains, will surely affect signal transmission. Although PMD is random and hard to measure, long-distance links are tested to ensure that any existing PMD is within a range that can be tolerated by the system. The impact of PMD in optical link performance is correlated to data transmission speeds, so the higher the data rate, the more sensitive to PMD. Single-mode fibers have undergone significant innovation over the last few decades. Since the late 90s, new fibers have been developed to overcome issues with absorption, reduce attenuation, as well as dispersion. Among the most important developments in fiber innovation are the low and zero water peak fibers, with water peak referring to the wave-shaped spike in the attenuation curve over the 1,400 nanometer wavelengths range, which is the most impacted by absorption. Low and zero water peak fibers have been improved with manufacturing techniques that reduce residual water vapor molecules causing absorption in the fiber to increase transmission capacity. Other advancements in optical technology include fibers with reduced dispersion that enable increased distance reach. Also, recent techniques to increase bending tolerance for making fibers more resilient to attenuation from physical stress.